So constant pressure calorimetry, and this is what we're going to be doing in lab today. So we can measure the enthalpy change or the heat of reaction for many aqueous reactions in a very low-tech device, a coffee cup calorimeter. And this literally is a styrofoam coffee cup. Well, two styrofoam coffee cups. Two nested styrofoam coffee cups. Two is better than one because better insulation. In a calorimeter, you don't want heat escaping through the sides. You want all the heat of reaction to stay inside so it changes the temperature of the liquid. This one's fancy. It has a cork lid. We have cardboard lids that are older than dirt. Some of them are like 30 years old, literally, so be in awe. Thermometer. We're actually not going to use a glass stirrer. We're going to use the thermometer to stir, and we're going to do that carefully. So in this coffee cup, it's open to the atmosphere, right? There's a lid on it, but that's not airtight. So the pressure in the coffee cup is the same as the pressure outside. The pressure's not changing. Under constant pressure, Q solution is the mass times the specific heat capacity times the change in temperature. And this is what we can measure. There's water in there. The reaction is occurring in the water. The water absorbs any heat or provides any heat that the reaction gives off or takes in. Q for the reaction is the same value as Q for the solution, but opposite in sign. So whatever the reaction gives off goes into the solution. And at constant pressure, Q reaction equals QP, which is the heat of reaction. So if we want the heat of reaction in kilojoules per mole, then we'll take whatever we calculate for this specific reaction that we did and divide by the moles of reactant and get kilojoules per mole. So let's look at an example. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.4 degrees Celsius to 24.21 degrees Celsius. Calculate the heat of reaction for the reaction as written. Use 1 gram per milliliter as the density of the solution and a specific heat capacity of 4.18 joules per gram degrees Celsius. Okay, so let's think about what we've got here. We have 50 milliliters of 0.1 molar of the silver nitrate. And we have 50 milliliters of 0.1 molar HCl. And we're going to mix those in a coffee cup. So here's our coffee cup. If I put 50 milliliters of one solution and 50 milliliters of another solution, what's the volume of my solution? 100, right? So I've got 100 milliliters in here. There's a temperature change. So it says, the initial temperature of the solution from 23.4 to 24.21. So initial is 23.40 degrees Celsius. Final is 24.21 degrees Celsius. Can we calculate delta T? Sure. Delta T is the final minus the initial. I don't trust my brain to do that one. Whoops. 24.21 minus 23.4, 0.81. We are trying to calculate the heat of reaction. The heat of reaction is equal to Q reaction, which is equal to negative Q solution. So that's the mass, the specific heat capacity, and the change in temperature. We get the change in temperature. We don't have the mass, but we have the volume and we have a density. So we could calculate the mass of the solution. 100 milliliters times 1.00 grams per milliliter. So our mass is 100 grams. Right here we have the specific heat capacity given to us. So we have delta T, we have the mass, we have the specific heat capacity. We have everything we need over here. So plugging those numbers in, I'm going to keep this negative sign out here. The mass is 100 grams, specific heat capacity 4.18 joules per gram degree Celsius, and temperature change is 0.81 degrees Celsius. So this is negative 338.58 joules. Does the amount of heat given off depend on how much stuff reacts? If I burn a teaspoon of gasoline or a gallon of gasoline, is there a difference in how much heat is given off? There is a difference, right? So this is the heat given off when this amount of stuff reacted. So useful, but only for this particular situation. It's more useful if we figure out this in joules per mole or kilojoules per mole, right? So it's asking for delta H for the reaction as written. So delta H reaction. We're looking for the heat for how much silver nitrate. The chemical reaction says 1 mole, right? Well, how many moles of silver nitrate reacted? We've got 50 milliliters and 0.1 moles per liter. We can figure that out. I'm going to make some space up here at the top. $50 milliliters. Oops. And convert that to liters. And then multiply by 0.1 moles per liter. I should be able to do that one in my head, but you know, daylight savings time. We'll blame it on that. So the volume and the molarity of what I reacted here allows me to calculate how many moles of silver nitrate reacted. Everybody okay with that? Everybody's very dead this morning. It's really just a dead audience here. How much of the other reactant do we have? It's actually the same, right? We've got 50 milliliters, the same volume, the same concentration. We could do the same calculation and we'll end up with the same result, right? So 0.00500 moles of HCl. So does it matter which of these we look at? No, because they're the same. And in the equation, it's one of these to one of those. So we're looking for the amount of energy absorbed or released when 1 mole of this reacts. But we didn't have 1 mole react, we had 0.0050 moles react. So this was the amount of heat for 0.00500 moles. So if I divide by that, that will get me the energy in joules per mole. So I'm going to take my 338.58 and divide by the 0.005. And I get a really big number. What would probably be a better unit to express that in? Kilojoules. So that's going to be, and we should have 2 sig figs in this whole thing. So negative 68 kilojoules per mole. I rounded. So I moved the decimal point 3 places to do the kilo, and then the 7 rounds this 7 up to an 8. And so my answer up here is negative 68 kilojoules. Any questions? Clear as mud, right? We did a lot of practice. Here's a conceptual question. We have the same reaction, exactly the same amount of reactant. We're doing 2 identical reactions, one in a bomb calorimeter and one in a coffee cup calorimeter. Remember, the bomb calorimeter has constant volume, but the pressure may change. The coffee cup calorimeter has constant pressure, but the volume could change. So for one of the calorimeters, we got Q reaction as minus 12.5 kilojoules, and in the other, minus 11.8 kilojoules. Which one came from the bomb calorimeter? We're supposed to assume that the reaction has a positive change in volume. So remember we talked about energy or being heat plus work, and the work could be pressure volume work. Yes?
Which one allows a change in volume?
The coffee cup. Because in the coffee cup, like if gases are given off, they can just expand. In the bomb calorimeter, it's sealed, it's airtight, and so the volume has to stay the same. So in the coffee cup calorimeter, this P delta V term is not allowed to happen because it's sealed. In the coffee cup, we can have this term happening, and it says assume that the change in volume is positive. If delta V is positive and there's a minus sign in front of this, what's the sign on the whole term? Negative, right? So we've got Q minus, I'll call it X, something, right? So this is for the coffee cup. So Q minus X versus Q for the bomb. Which one's going to be bigger? The one that has nothing added or subtracted, or the one that has something subtracted from it? This one has to be bigger, right? The bomb calorimeter one. It's too early in the morning for a problem like this, isn't it? Yeah, so then we look at this and we're like, well, yeah, absolute value bigger or more positive, more negative? What are we talking about here, right?
So the Q would be negative and X would also be negative, so that would end up being negative 12. Because you're adding.
That's an excellent thought. So this, one of them is one of these and it's negative. So we know that this Q is a negative number. Let's call it negative Y. And so if we have negative Y and we're subtracting something, it's going to become more negative, right? So the one that is more negative would be A.
So what are we asking for the bomb?
Oh, I didn't put the answer on there. Nice. Pardon me?
It's asking about the bomb. Yeah. So wouldn't it be B? Because the top one's coffee?
Yes, thank you. I missed something. Yeah, it's not which is, I don't know. Can we start today over? Which value was associated with the bomb calorimeter? And I answered which one was associated with the coffee cup. So this is the coffee cup. I can't even write. And there's the bomb one. Yeah, let's just forget that ever happened.